We are talking about Chapter 2, and this is actually our second video. Chapter 2 is going to have, I think, about 4 videos. So we'll pick up with this, our second video in Chapter 2. So let's start out with acceleration. We have talked about velocity and average velocity. Instantaneous velocities, the velocity at any point in time, and the average, of course, is an average of, in our case, 2 different velocities. But we want to see how that ties to acceleration. So acceleration is what changes your velocity. Acceleration is a vector, so it has magnitude and direction. It has both magnitude and direction. And you can speed up or slow down. So slowing down is usually called deceleration. The velocity and the acceleration can go in the same direction or they can go in opposite directions. Obviously, if they're pointing in opposite directions, you are slowing down. So let's look at some of these. The acceleration is the rate and change of velocity with time. Anytime you hear rate in an equation, definition of a value, rate means you're going to be dividing by time. So acceleration is the rate of change of velocity with time. So acceleration, in our case, it'll be a lowercase a. We start out defining it with the bar over it, but we're going to leave that bar off almost right away. So acceleration is change in velocity over change in time, so delta v over delta t. Remember, change in is final minus initial. So final velocity minus initial velocity divided by final time minus initial time. Almost always, our initial time is 0. I don't know why I've got a t sub I there when we've got a 0. You have i's or zeros. Maybe I made the mistake so I could remind myself to tell you, I don't care if you use an I for initial or a little 0 for initial. Doesn't matter to me. I apologize. That probably should have a sub-0 in it. Let's see. I can't edit it easily, so we'll leave it there, but it could be a sub-0. I'm so sorry for the mistake. All right, so we're going to be dealing with accelerations. Again, can be positive or negative, can point the same way as the velocity or opposite. So, and deceleration's always slowing down. So we'll look at this little graphic from the book. Here we've got velocity, which is the green arrow, and acceleration, which is the purple, going in the same direction. Here we have them going in opposite directions. That means this car is slowing down. In this next one, number C, we have them again going in opposite directions, but that's because we've got the car going left and the acceleration going right. And then the last one, we have them going in the same direction. They're both, if we make to the right positive, they're both negative. So the car in this case is speeding up, it's just speeding up in the negative direction. The box helps you, I think, understand what's going on. So we're probably going to always define the direction the object moves in as the positive direction. That means that negative accelerations will be decelerations. They'll slow us down. If we look at position versus time, velocity versus time, and acceleration versus time for an object, we can see how these graphs give us information. So again, title at the top. Each axis has a title with the units of measurement in parentheses. So time with seconds in parentheses, position with meters in parentheses. The graph starts at 0. The x-axis and the y-axis do not have the same units on it. However, they do change uniformly. So if we go from 0 to 10, 10 more would make it 20, 10 more would make it 30, and so on. On the vertical axis, we go from 0 to 50, 50 more would make it 100, 50 more would make it 150. You cannot change the magnitude of your divisions, your marks, just on a whim. Once you pick one, in this first case, vertically, we made it 50. Every one after that is just 50 more than the one before. So be careful. So we've got our position versus time. We're starting out. We reach a standard rate, and now we're slowing down. So speeding up, achieving a standard speed, slowing down. We can see that by how much distance we travel and how close the dots are to each other. Here they're really close. So when your position versus time graph has your dots really compressed, there's a rapid change. All right, so let's look at that. We've got the velocity was positive. This central part where we had a constant velocity because our dots were uniformly separated, we had a constant velocity. And here we are changing more rapidly. We're slowing down, but we're slowing down rapidly. So we can tell a lot how they compare. Here, if you look at velocity and compare it to acceleration, the first part of the graph, it's a constant velocity and it's positive. The middle part where a velocity is versus time is constant, we have zero acceleration. And then when we are going in the opposite direction, we have a negative acceleration, but it's a larger absolute value than when we started out. So we can get a lot from a graph if you just know what you're looking at. So do notice that acceleration is measured in meters per second squared. Do notice that acceleration is in meters per second squared. It's written down, but I didn't emphasize it. Acceleration is in meters per second squared. All right, back to the graphs and moving forward. So what equations do we need to know? You need to know that actually we really don't use this first one very much at all, but we do use this version of it. So remember we said if average velocity is delta x over delta t, well, average was final plus initial over 2, so we could write it like this. This actually is the version you use a lot. Delta x over delta t is v final plus v0 over 2. We also use acceleration is change in velocity over change in time. So v final minus v0 over t final minus t0. You can see I fixed that pesky in the previous video, or I guess earlier, it was a sub I, and now I've changed it to a sub 0 to make our nomenclature consistent, to make our symbols consistent. And again, I don't care if you use I's or zeros for initials. Doesn't matter to me. And now we want to introduce a new equation we haven't had before, x equal x0 plus v0t plus 1/2 a t squared. So this equation is probably easier for people to use if we write it like this. Take and subtract x0 from both sides. So we'll have a delta x, change in position, is equal to initial velocity times the change in time plus 1/2 multiplied by the acceleration multiplied by the time squared. The t's in this equation are the same as the delta t's in these other equations. I don't know why they chose to leave the delta off, but they did. Now there are people, so you really need to know 3 equations. You need to know delta x is v0t plus 1/2 at squared. You need to know that acceleration is v final minus v initial over t final minus t initial. And you need to know that delta x over delta t is v final plus v0 over 2. Those 3 equations. Some people include these 3, but it's really not necessary. They're all variations of those other 3, and so it's really not necessary to remember them. How are we going to solve? You can if you want to, but it's not required. So to solve a problem, you want to read the problem And if it looks like a picture would help you, you want to draw a picture. Sometimes it's useful, sometimes it's not. But it is really important to make a table of what you know, what you're trying to find, and you want to make also a column for formulas, because I tend to forget I know a formula in the middle of a problem if I don't write it down at the very beginning. So you just want to summarize. A summary to start out with. Organizing your information is really important. And you'll see we'll work every problem that I use for examples using this technique. Draw a picture if we can, make a table, fill in the table, solve the problem. So in the next video, in video 3, we'll use this technique to solve some problems. So we'll stop for now to get those formulas straight in your head. And then on the next video, we'll solve problems.